G'day people, just going to show you how to wire up a house, just in case you ever have to do it, or at least design it. And you may well have to do it or design it pretty soon. Okay, so here's a simple plan. 1-bedroom apartment, bedroom, bathroom, lounge, kitchen, little hallway. All right. And this is where the electricity is going to come into the place, right? Before they build it, right? This is where the fuse box is, right? So the electricity is going to come in there from the power line out on the street and go back out to the power line out on the street via the same spot. Of course, it has to go in and then come back out again because the whole thing has to complete a circuit. Right? And in this case, normally we draw a battery for the voltage source. Here, the battery is way back up there in the power station, miles away. Right? So this is just the very dead end of a very long circuit that may be a couple of 100 kilometers long. Right, so electricity has to come in and go out. And those of you who know your words will know that the electricity comes in via the active wire and goes out by the neutral. And there might be an earth wire involved as well, but we don't need to worry about that for now. All you need to know is what an earth wire does to save you. Okay, so if we're going to wire this up, we're just going to do the lights. So the people who have bought this thing off the plan have asked for 1 light in the bathroom, 2 in the bedroom, 3 in the lounge, 2 in the kitchen. So here's how we're going to do it. They're going to be wired up in parallel, right? So when they say they want 3 lights in the lounge room, they want one switch to turn on 3 lights in the lounge room, right? Flick the switch, 3 lights go on, flick the switch again, 3 lights go off. And no other lights go on in the house. You should know by now that we're going to wire this up in parallel so that the lights work independently of each other and so that they get maximum brightness from the voltage that they've got, right? So we're going to make this big parallel circuit. And it needs to be able to have a light in the bedroom, there. So a parallel circuit is essentially a ladder. Let me just get another spare sheet for a second. I'll get back to this. Parallel circuit is essentially electricity goes in, electricity comes out. Normally we sort of draw a battery there because we don't have a power station. But there's a light there, there's a light there. Right, so it looks a bit like the rungs on a ladder. And if you put a switch there, that switch will operate that light and it won't turn those ones on either. Right? If you put a switch there, that'll turn everything off or on. Okay, so this is the sort of thing we're going to do. We're just going to have to flex it a little bit so that it covers the rooms of this house. So here's the place. So I'm going to basically just extend this out along here. We're doing this really rough. I don't have to go. I know the wires are really inside the walls. We never see the wires, but we're just doing a concept here. So I'm just doing enough. That's my curved ladder. All right, don't join it up yet because you're going to have to put the kitchen lights there. So I might start that first. 2 lights in the kitchen. Okay, here's the kitchen. 1 light, 2 lights, and a switch. Don't forget the switch. So here's a switch to turn those 2 kitchen lights on. At the moment, everything's off, but as soon as you close that, flick it down, electricity can come in, go through the lights, go out again, lights go on. All right. So that only controls those 2 lights. Lounge room, 3 lights in the lounge room. So we need to have a bridge across here, across the lounge. And again, they might, in reality, this wire can be, flexed as much as you want so that the lights can be anywhere. But we're not worrying about positioning in particular. We're worrying about how everything's connected. So all we need is 3 lights on the 1 wire and a switch to turn them on. Okay, so now if we walk into this place and flick that switch, the lounge lights are going to go on and the kitchen lights are going to stay off because we haven't touched that one. If we walk past the lounge room, go to the kitchen, turn that on, right? These guys will get electricity because electricity can go through there. But these guys will stay off because we left that off. All right, independent of each other. Same thing with the bathroom, 1 light in the bathroom, okay. There's 1 light in the bathroom. There's a switch. And again, that will let the electricity go from the active through the bathroom light back to the neutral, right? Only when that closes. And the bedroom, they wanted what? Where are we? Bedroom. 2 lights in the bedroom, okay. There you go. So that's pretty much done that. This is the design of the wiring. Right? And each of those switches will only work for the lights that are in that room. That's really important. So if you walked in and just went straight to the bathroom, turn that light on so the switch is connected, right? The bathroom light goes on because now electricity can go through there. There's a contact. But it can't go anywhere else. It can't go through the bedroom because that hasn't been switched on. Can't go through the lounge. Can't go through the kitchen until someone flicks those switches as well. Right? So it only turns electricity on and turns the light on where we want it. Okay, one more thing. A circuit breaker has to go through here. A circuit breaker is something that stops electricity from coming into the house at all under two circumstances. Firstly, if too much electricity tries to come in at once, like if you've got all the lights on at once and the toaster and the oven and the kettle, you might be sucking in so much current that it could melt the wires. And that can't happen. So a circuit breaker is put here to stop too much electricity going in. And the other thing it stops these days is it also stops it also blocks all of the electricity to the house when there is a difference between how much is coming in and how much is coming out. Because if there's 10 amps going in, then 10 amps must be going out as well, right? The outside is in series. What goes in must be coming out. If there's a difference between what goes in and what goes out, then some of the electricity is going somewhere it shouldn't be going, like through a human body, for example, or to the outside of a toaster ready to electrocute somebody, for example. So it also shuts off the electricity then. Now there's a symbol for this, and I'm going to draw this really small, and I'm going to draw it big so you can see it. But that is the symbol for a circuit breaker. I'm going to do a big one here. Just zooming in on there. If you had to do a symbol for a circuit breaker, this is it. That thing there means a circuit breaker. Something that will trip and stop the current going in if something is going wrong. All right. Now, by the way, at the moment, if all these lights are equal, one last thing, that light is going to glow brighter than these ones because they're all getting 240 volts, right? In Australia, every single house gets 240 volts. So when you turn that on, that one light is getting 240 volts of voltage. These three, when you switch that on, 240, 240, 240, and the 240 volts has to get shared between three lights. So they're only going to get 80 each. So if those lights are the same as that light, they're going to glow a lot dimmer. Right? So the lounge room better have different design lights that can go bright with only 80 volts each because that's all they're ever going to get. Right? This is why different lights are for sale for different applications. If they were all the same, different rooms would be different brightnesses. Okay, my friends, I'm out here.